dislocations. So that's why I probably go back a little bit, or maybe later during the question. So in the TEM images, in the high resolution, we see very high number density of precipitates compared to the ultrafine grain material. So have understanding all those microstructures. Now let's look at the quantitative values in the strengthening mechanism. I kind of covered the whole patch overall strengthening from here. But in this complex system, you still have solid, some magnesium, zinc, and copper is in solid solution in the matrix. So you also have a solid solution strengthening and also the work hardening from the dislocations due to the deformation. So in terms of really giving a sense of value of each mechanism contribute to the strength, we need to have quantitative value for like the grain size, for the interspacing, interprecipitate spacing, and the size of precipitates and the volume fraction here. So that's some collaborating work I have been established with Northwestern University, where they use this technique called atom probe tomography, can help you to identify the chemical of each atoms, which I only showed, again, one sample here, but we made a lot of samples because those samples are narrow pillars. If you want to really get a sense, you need to make a lot of samples and calculate them to get a more statistical value for here. Anyway, combine the TEM and then the APT, I do get a quantitative value for the microstructure features here. And applying all those values back to the equations I showed previously, we can now get a sense what each mechanism contributed to the strength here. So we see for those as extruded condition, the grain boundary plays really an important role in the ultrafine grain materials if you compare the value. After T6, in this ultrafine grain material, grain boundary strengthening is still very important. And at the same time, this is just theoretical estimation of the values. I'm not saying in reality those values add up, and that's the question I said at the beginning, right? Right now, some of the researchers, they do this and they just add up all the values, saying, yeah, this is the strength I'm going to get. Guess what? This is not. So we need to really understand what's going on in those microstructure, and you can try to investigate what each mechanism give you, or theoretically can give you. But once you have so complex system, are they just add up to each other? Or are they, I will not really say they compete with each other, but as we see the precipitation behavior, the grain boundary did change the precipitation behavior. So which kind of reduce the strength you can get from there. So which give me motivation for additional work. So it's going back to triangle. Now I use some processing, achieve some microstructure, look at their properties, so I know what's going on here. Now can I go to the reverse way? If I want more precipitates in an ultrafine grain material, what should I do here? So then I go back to think about the processing. Can we try to retain those dislocations within the grain matrix or not? So we need to think about some code work, right? We need to reduce the temperature here. So which giving me another processing route we using, we call it a high strain rate extrusion at room temperature as the last step for these materials. And this is what I get. The curve one first, very impressive improvement, like a little bit improvement in terms of mechanical properties again. But there's still things interesting going on here. We have the uniform elongations. But if we compare the curve 1 to 2, now 1 is the extruded condition. 2 is the T6 temper. So it's showing you the reverse, what we learned from the previous, which is not what I expected, but which actually now give you a room, if now you care more about ductility than strength. You still have a way, you have a method to achieve that. So that's why I would like to also highlight T6 increased ductility of the high strain rate formed material. So again, we always cannot avoid to study microstructure. First, I want to confirm what I want. I did get a coupling of dislocation and precipitates using this processing. So this is the extruded condition, and you see a lot of deformation and dislocations in here and associated with your precipitates. So I do, choosing those process, I do is seek to get coupling of dislocation and precipitates within that grain, not at the grain boundaries. And we also want to figure out, okay, now we get even better uniform elongation. I didn't point out, but maybe some of you noticed for those materials showed previous, there's a little stress drop after yield pointing there. But here you now see more uniform elongation. It's because now we formed sample place lamella structures. They are still formed about several grains string up, but the grain boundaries between them are very low angle grain boundaries. So it's like smaller than 5 degree or 10 degree here. And those low angle grain boundaries allow the dislocations to glide through those sub-grain boundaries or low angle grain boundaries, so which allows you to accommodate more dislocations within that lamella structure, which give you the better ductility. Ductility is where you can deform the material without breaking it. So I'm going to skip this again, like I'm not going to details, but we do look at after T6. So you see the comparison here, using a traditional extrusion, we get higher number density of precipitates. But using this after T6, we get coarser, a lower number density. So this gives me an idea about the design, right? What's the desirable microstructure if we target at higher temperature, higher strengths here? So we hope, like using some high rate strain rate deformation, we can end up with still grain boundaries, give you a grain boundary strengthening. But there are some along this direction, you can have low angle grain boundaries here, which allows you to accommodate dislocation for ductility. And inside the grain, you have this coupling of dislocations and precipitates will give you a higher strength there. So it's kind of a recap, again, a recap of this aluminum zinc matte copper alloys. We start with, design of some TMP process giving you higher strength, but we find, and especially for scale up of the bulk nanostructural materials, and then we find the interesting phenomena that the nanostructure not only increased the strength of materials, however, it changed the precipitation behavior in this material, which didn't give you the high strength we expect. But we end up, going back to the process design, and then we can find a coupling of dislocation and precipitates in those ultrafine grain materials can give you further room for improvement in strength. So I know I'm going very fast, trying to give you an idea about what previous research I have done, but that's not only this. So I'm also want to share very quickly 2 slides showing I'm also doing computational work using like a CalFET, the calculation of phase diagram method using thermocalc, help you to understand the equilibrium phase fractions in that nicroid system I talked about for the thermal barrier coatings, and also how adding iron into this can change the phase here. And this is another simulation I have been doing to using an MD simulation to study the interface behavior between aluminum and aluminum oxide. If you recall, after cryomilling, we get a lot of aluminum dysbiosis, and it's still a mystery how we form those aluminum nitride in this material, because the liquid nitrogen molecules, they have triple bonding here, very strong. You need to break that and then to form the aluminum nitride. So my simulation work is kind of only provide some insights here. To me, this question still remains. I'm interested to look further into that, how we can form institute, kind of an institute formation of aluminum nitride just during ball milling there. And I also have collaborated with a lot of people doing some other side projects. So this is collaboration with Professor Devanir at UC Merced, where I help them to using narrow mechanics, narrow indentation, to probing the structure and mechanical property of some narrow porous diatoms. They trying to engineer narrow templates for biomedical engineering here. And what I have been doing is that I help with the experimental part to characterize them and also do the nano indentation, giving them the value of the Young's modulus and harness, which her student can apply to the simulation to simulate the strain field once you load something on this template. And I also have been very actively involved in some institute work here. So this is back to the aluminum 7000 series alloys, where we make single crystal. So we cut the sample to narrow pillars, which only contain 1 gram, but you have narrow precipitates inside. And I don't think the time allows me to really play the video here. But what we do is put the whole sample and the probe inside the TEM, and then you deform it while you observe what happens there. And for a single crystal without grain boundary, we see this continuous in a stress curve, which literally called the strain burst, because now the dislocations can escape from the surface, because these are in the size, the pillar is in the size of 200 nanometers here. But once we get a multiple crystal, so if you introduce both grain boundaries and precipitates in this narrow pillar, now we can get rid of that strain burst phenomena, because now the grain boundary rotation also become active in this material. So in addition to that, I really have established a wide network to doing my collaborations. So in addition to my advisors, and then Dr. Ali Yusufiani from Boeing, and he has been very supportive to my research, and I'm very willing to continue to support my research once I find a position. And Dr. Bill Gorompolsky from Office of Naval Research is who support our very big program in the aluminum multiple scale composites. And there's also Dr. Wei from University of North Carolina. We do those dynamic compression tests on the samples. I'm not going to read all those, but I believe those network I have established will be very beneficial to my future research here. So now it's coming to what I am doing right now at UCOI. So in addition to the alloys, now we also introduce boron carbide particles to the aluminum 7000 series composites here for stiffness, and also because boron carbide is as light as aluminum, so you don't increase the weight of the materials here. So we started with kind of a theoretical design of these trimodal composites, where you can even manipulate the distribution of the B4C particles, either get narrow particle homogeneous distribution, or it's a more micro-sized design here. And even this, you can make it into a fiber-like ridge zones, or just a spherical ridge zones of this. And here is where we can introduce force building block. We have the coarse grain powder, and we have this narrow structure powder, where when we do the milling, we also add the B4C in it, so create different level of interface. And this is something the Office of Naval Research, they are interested in investigating how we can make a composite plate which showing ballistic behaviors. So now I'm really showing the plate I'm making that it's big, which and thick you can show them. That's where I'm talking about the scale up here. And this is a real microstructure compared to the design we were talking about at that point. And this is still going on. And some of them is not published yet, so I cannot continue too much detailed results, but it's just giving you an idea about why I have been interested in doing design microstructure for desired properties. In addition to this, during all the process, I also have been thinking about the challenging we have using the whole powder metallurgy and consolidation methods. It's really a long run cost to energy time here to go through all this. And at the end, you still need to machine your material to the desired shape. How can we really make a more sustainable processing here by using the additive manufacturing of metals? So that's what another project I have been I'm working on currently. We use the laser engineered net shaping as where you use the laser as a power and then inject the powder through the gas stream. At the same time, you use a computational aid like control, so you can move the stage to create layer by layer the exact pattern you would like to make. And these are just the examples about how complex 3D component we can make without machining. That's why we call it near net shape components here. And previously, we are more at the stage of exploring the capability of the direct deposition. And right now, we are working on, okay, now you make this. what's the mechanical property here? Did they break easily? Then that's no nonsense to make it. So we are not right now. What happens to examine mechanical behavior of those deposit hard and microstructure integrity, and also influence of the feedstock powder, because you can use different size of the powder, different morphology of the powder, different internal microstructure there. So I think this is the challenges I'm aware of, from my all the ongoing research. You already see that the bulk neutral metals alloys increasing strength will accompany by the sacrifice of ductility. And I'm talking about the sustainability of this process. Even now using the additive manufacturing, people find out low deposition efficiency in this lens process technique. Also will kind of give you the statement about, people have been claim additive manufacturing is sustainable processing because now you are adding materials instead of substrating materials. But the reality is you put 1 kilogram of powder in your powder feeder, you deposit your parts. How much of that 1 kilogram powder go to your parts? How much powder are left on the stage, right? Can we reuse those powder or not? So this become another issue when people, now it's very hot topic, people claim it's very sustainable, but we still need to fully investigate this. And all those direct to my future research directions here. So for the sake of energy saving, I know now people investigate like biofuels or solar cells, those are saving the energy. But from, for aircraft, for transportation, there's still a long term, people need to use traditional fuel. So to making light and strong materials still very important, at least in the next 10 or 20 years. And one of the talk I attend given by the director of Army Research Lab, he also specified this bullet, saying light and strong materials are still the interest of Army Research Lab here. And the second, it's more long-term, is how we can combine the benefits of the metallic 3D printing to the nanostructuring I have found, from those powder. Because I'm aware, all those additive manufacturing, they melt your powder, right, before you form that parts. How can we sustain that benefits I got from the nanostructure powder? Can we do something like either modify the process parameters, or instead of doing that melt and pour, can we do sintering instead? You're still using laser or maybe sometimes e-beam as a source to generate a very quick or rapid sintering of your powders, so you can retain at least a part of the nanostructure in your parts, which is still giving you higher strength and other properties here. So I would just like to show you this. My future research still will be this, to investigate the correlation between these three as still the core. And I will also like to establish real computational work to assist, my work here. And this is just showing you my idea is not really something it's not just very theoretical. Actually, Airbus, they recently showcased this 3D printed airplane cabinet component.
How big is it? What's the size of that?
The size of it's a real cabinet, so it's kind of as high as one where you can see from the roof here. So, but they are using traditional gas atomizer powder, not the nanostructure powder there. But that's something I would really like to further investigate. And I hope I don't run out of time here. And then here is where I talk about the sustainable material use in additive manufacturing. So we don't want to waste the powder. If we are using powder as a feedstock, we need to make sure the powder left over on the stage can be reused. So I already start to conduct some preliminary results to characterize those powder. Now I define it as virgin gas atomized powder, and which is not really a waste. Now I'm just using this term, which is sitting on the stage. Look at both the morphology, the size, and the internal microstructure of them. It turns out if we can perform either some grinding or sealing of those materials, we can reuse them, right? Not only once, maybe twice, 3 times. And that's why my PhD advisor and I, we recently submitted a proposal to NSF SysChem, to see whether we can pursue joint of interest to continue this work. And this is the schematic that I'm showing, the difference in terms of feedstock powder you have virgin, and this is the waste powder. And now we can even think about the machining chips, where we can collect them and apply them in those additive manufacturing. So this brings me to the grant writing experience. So I have been going really long way in postdoc research. I don't only just doing my own research, I mentor students, I writing proposals, and I'm also teaching as a lecturer, which I'll talk later here. But I have, this is very small amount, like a subcontractor with some Air Force Phase 2 through a company at California, but which allows me to pay myself a little bit, doing some characterization for them. And this is the proposal I just mentioned. Submit, and we hope we can get positive results there. And because I'm interviewing right now, and I do talk to my advisor about this, so she's very positive and supportive, how we can not really split money, but I can probably bring part of this and continue our collaboration if we get this project funded. And I also have writing several white papers to the Office of Naval Research, which unfortunately haven't gotten approved, but giving me a lot of experience to writing this. So the target funding sources. This is the big one career I will aim for, and I know it's competitive, but I will make whatever efforts I make for this National Science Foundation. And in terms of equipment, or I mean after 2 or tomorrow, I might get a better sense about what equipment I need. And I'm not saying like I just need the department or university provide whatever I need. I will also really like to collaborate with the existing faculty to see whether there's some bigger equipment both of us need, so we can compose MRI program together. And I would like to use my network previous to see whether there's any funding opportunities from the Army, from ONA and Boeing, and any other possibilities from the conversation from faculties today. And I know there's industry called the Lockheed, something which might use my research a lot, so I can start to connect with them looking for fundings. All right, research. So now I'm talking about teaching here. Yeah, the research actually is very close related to what I have been teaching. I taught an up-level undergraduate class at the UC Davis, which is called Materials in Engineering Design. You already see part of that. I integrate the material science to their engineering design process. So this class talking about how we can perform material selections, process selections, and also integrate the green engineering, thinking about the life cycle. So when you make a product, don't end your thinking when the product comes out. You need to think about what happened to that product towards the end of life. Are they hazardous? Are they going to consume energy to dispose them or not? So that's the green 3 parts: materials, process, and green engineering here. And here I'm just showing some example teaching materials here. This is again like the material property charts, helping the students understand which region is our select region according to the design requirement here. And because we see still white space in some in those charts, there's where I introduced the design of composites. Sometimes when a pure metal, not pure metal or ceramic itself cannot give you a design, now we can make composite to getting the properties you need. And this is an example about how we think about the life cycle. You don't only just stop about the product manufacturing. You also need to think about the use of the product here, how much energy it will cost. And when you select process, it's not only thinking about the compatibility between the materials and the process. You also need to think about the cost modeling in this, and then combine the green engineering. So it's a lecture plus discussion course. So we have 1 hour discussion every week where we're really talking about detailed case studies. So I will give you more real examples, thinking about different situations and how that will affect our objective function, and then what's the dominant phase of the life, which end up giving you different criteria, and we need to explore different materials and process for that. So considering my research background and my teaching experience, I'm comfortable to teach the material-focused in a class in the current curriculum here. but I'm also very interested to develop a new class, especially to using, some software to help the mechanical engineering students understand how to select materials, how to perform their engineering design. And at the end, I would like to acknowledge my advisors again and the funding support my research. And thank you all for your attention.
Question?
Yes.
Where do you actually get the powders that you then cryomill and everything? Where do those powders actually come from?
So we have two resources. First, our group have an in-house gas atomizer.
Okay.
So we can just buy chunk of materials and then making the right alloys and then using atomizer to produce the powder. Second, like the engineering material I have studied, because they are already available commercially, so we can just buy them. And those are like less costly than we making them. But there are some special alloy compositions, we made them in-house. Yes.
Did,
Huh? Yes.
did you compare your T6 UFG to a T9 in the conventional grain size?
I usually try to compare the coarse grain and ultrafine grain material in the identical conditions.
Right, but you've already cold worked essentially your ultrafine grain, so I mean, it would be interesting to see what the T9 condition properties of the CG look like.
Yeah, there is, I have some work trying to look at the heat treatment, because my conclusion is those standard temper probably doesn't apply for the ultrafine grain materials. I didn't put a slide here, but I have a paper talking about if we shorten the heat treatment, it's not extend the time, it's shorten the time and lower the temperature. We will give you more precipitates there. So we do need to think about the tempering, that's very good. You brought up that. Yes.
So where are these two technologies that you talked about, the bond coat and this aluminum alloy, how far is it in implementation? Or is it being implemented in the industry?
Siemens, like one of my, it's also when I was a student, they used the powder we generated to make the coatings here. And I think it's the corrosion, when they're talking about the corrosion resistance, that doesn't, at that point, it doesn't meet the requirement yet. But they do, they are aware of this, but it's because the thermal barrier coating community, against the funding problem, they have been, become peaks, a lot of people working on that, and then towards the end of my PhD work, it's getting to another peak, and that's why I didn't continue to that work over there. But I believe if we can have, find funding to continue modify, again, when we do material science and engineering, it's not possible you can just get a perfect material just in 1 year or 2 years. We always learn things from here, investigate, and then going backwards to see whether we can further design for this. So it's not, but in Boeing, they're also now making those small parts, not really applied to an airplane yet. But they are making those parts.
So in your laboratory, do you also do the flame spraying, so you do the ionization to prepare some of the materials? The flame spraying coating, is that done by you or?
Personally, I didn't do that. So I collaborate with Plasma Tech, which is a company in Southern California. So I travel, so I visit them, bring my powder, and then I was with them, about the process parameter selections on those.
If you had, would you like one if you could have one? Would that be something that's useful, or is it better just have?
It's better to have one in-house, so we can really control. So you can really control the process here. The answer is different.
Would it be better to do plasma spraying or flame spraying, or do the company do both?
The company is doing both, but at that time I'm using this, the high velocity oxygen. It's sometimes, when we're doing research, it's always trade-offs, to looking for commercial resource, you can get your results very quickly or something, but you lose the control of the process. And sometimes something happens during the processing, you don't know. But if we have the equipment in-house, you need to spend time to maintain them, you need to set up them, which give you a benefits really to control the whole processing here. But I think for me it's better if I can have one because that's actually what I feel about the spraying. At this point, right now, people haven't really created very perfect, CAD profile but that's also something we can develop it as additive manufacturing, 3D printing, if we can combine the computational. It's spray using dynamic instead of melting your material. There are cold spraying right now also. They use very high speed injection of your powder, so the powder is not melted, so where you can retain the nanostructure.
And then if you used a laser and electron beam as you were spraying, would that be interesting?
Yes.
Get to go see all his toys tomorrow.
Yeah.
Any other questions for Dr.?
How recent is your CES software?
You're
that
next.
you-
But, okay,
How recent is your CES software? That you-
Oh, you mean the software I'm using is 2014. So that's where I can get those green engineering database.
Go ahead, Jason.
If looking towards like commercializing the ultra-fine grain aluminum, what would be your biggest concern? Is it corrosion or fatigue or duct filling?
Fatigue is one of them. I didn't put it here, but that's as a more short-term research goal. If I find a position, I can bring all the materials I already have. So I don't need to buy, I like to look at the fatigue behavior. Because think about the airplane graph I showed you. The landing gear is made of those alloys. Every time when you take off and landing, we need to worry about the fatigue of this. So to really apply that, definitely we need to not only look at the room temperature mechanical behavior. The results I'm showing here is kind of a way for basic research to understand the correlation here. But definitely too, there's a long way to really put all those fundamental research to real applied research. And that's why I'm interested to continue my research to make this, realized one day.
So if you probe into Jason's question, and you said that, when you do the ultra-fine material, you lose ductility.
Yes.
But you don't necessarily increase the likelihood of fatigue, right? I mean, is it possible that crack propagation would be inhibited?
Grain boundaries should, theoretically, it should be a very good impact, stop for those crack propagation. But if you think once it's the crack, if it's propagate along your grain boundary, then that's another issue there. So, I'm aware of, that's why I'm trying to, saying I'm not here to making perfect materials. I'm here to increase or enhance the performance of the materials step by step, and also at the same time to understand the fundamentals, what's going on in this. So I believe one day, not only with my own efforts, the whole material science society will achieve one day we can really apply those benefits in there. And there will be process available to increase. And that's why, as I emphasize, you need to first translate your design requirement to the properties first, because you cannot have the best corrosion resistance, the highest strength, the highest ductility in one material. Maybe when we advance, when we make more advanced materials or composites, maybe we can get triple benefit.